A mixed integer optimization model for robotic warehouse stock keeping unit allocation and order picking efficiency. Modern warehouses are increasingly automated due to e-commerce growth. While robotics improves speed, the efficiency of operations still heavily depends on how products are physically arranged in the warehouse. Robotic storage and retrieval systems, autonomous mobile robots, and intelligent picking stations are now widely deployed to improve order fulfillment speed and accuracy. In such environments, the efficiency of order picking operations depends on routing algorithms, robot coordination, and special allocations of stock keeping units within picking zones. Today, warehousing is defined by how fast, precise, scalable, and resilient operations can be. The growth of e-commerce, rapid delivery models, and omnichannel logistics has pushed warehouses to adopt robotics to stay competitive. Technologies like autonomous mobile robots, automated guided vehicles, and robotic picking systems are reshaping how modern warehouses operate. Warehouse robotics refers to unmanaged machines capable of performing specific tasks within a warehouse with the aim of relieving human workers from repetitive and potentially dangerous tasks. The surge in warehouse robotics automation is primarily driven by advancement in AI and machine learning, better sensors and response capabilities, and the integration with warehouse management system software. Different types of warehouse robotics include automated guided vehicles, autonomous mobile robots, aerial drones, and automated storage and retrieval systems, each offering unique benefits. In this research, we investigate the structured stock-keeping unit allocation in robotic picking systems. The core problem is deciding where to place each stock-keeping unit in the warehouse. This decision must balance operational constraints and performance goals, such as minimizing robot travel and improvement throughput. The model introduces a stock-keeping unit family organization in which families represent growth of stock-keeping units frequently demanded together or grouping of stock-keeping units based on some similarity factors. The family structure is enforced through contiguity constraints and tolerance parameters that regulate the spatial consistency of stock-keeping unit families across multiple picking zones. This design enables the formation of structured storage blocks that reduce robot travel distances and support balanced load distribution. Most existing approaches ignore relationships between products. However, in reality, many items are frequently picked together, which suggests they should be stored close to each other. This work introduces SKU families, which are groups of items that are related. The model ensures that these families are stored in a structured and consistent way across the warehouse. The proposed formulation integrates zone capacity constraints, multi-zone allocation rules for SKU, configuration-dependent storage feasibility, family consistency constraint, supply minimum and maximum quantity requirements. We use a mixed integer linear programming model, which allows us to handle both discrete decisions and continuous quantities. The objective function reflects picking efficiency based on the demand and priority. The system consists of zones where items are stored, individual stock-keeping units, groups of stock-keeping units called families, and different ways items that can be physically stored. The model ensures that physical and operational limits are respected, such as space constraints and how items can be stored. The key constraints are zone capacity, width, height, depth. SKU limit quantities, minimum and maximum quantities, supply limits, configuration feasibility. The model ensures that physical and operational limits are respected, such as space constraints and how items can be stored. Advanced constraints are multi-zone allocation, balanced distribution, family contiguity, no gaps between zones. The problem is computationally difficult. Even simplified versions are reduced to well-known NP-hard problems like the knapsack problem. Moreover, when multiple picking zones are considered, the stock-keeping units can be assigned to several zones with capacity constraints. The problem generalizes multidimensional knapsack and bin packing problems, further reinforcing its combinatorial complexity. Despite its complexity, solving this problem leads to significant operational improvements in robotic warehouses. Why it matters? It reduces roboted travel distance, improves load balancing, better space utilization, faster order fulfillment. The structured allocation improves not just efficiency but also interpretability and stability of warehouse layouts. Coherent SKU placement, reduced fragmentation, predictable robot routing, stable layout. In practice, frequently picked items are placed closer to main robot routes, while less important items are stored further away, reducing congestion. Figure illustrates a sample allocation for a warehouse with two picking zones, three SKU families, and multiple SKU per family. In the example, high-frequency SKU are placed in proximity to the primary robot path and minimize travel distance. SKU families are located continuously across zones, respecting imbalance tolerance constraints, enable consistent access patterns. Low-demand SKU are assigned to zones further from main picking zones, reducing congestion and high traffic areas. The warehouse layout ensures that frequently co-picked SKUs are spatially near one another, supporting efficient batch picking and reducing the total distance traveled by robots. The proposed SKU allocation model provides several structural and operational advantages for robotic warehouse systems. For example, structural coherence of allocation, reduction of combinatorial disorders, support for robotic navigation logic, controlled spatial stability across zones, scalability of the family framework. This framework, in general, can be applied to other domains where items need to be organized efficiently under constraints. For example, production line, hospital inventory systems, library or archival systems. The effectiveness of the model depends on how well SKU families are defined and may require periodic updates as demand evolves. Future research can focus on faster solution methods and integrating machine learning to improve SKU grouping and adaptability. In conclusion, incorporating SKU families into optimization leads to more efficient and scalable warehouse operations. The central message is that introducing structure into how items are stored directly translates into a better system performance. Thank you for your attention.